So I spent the last lecture trying to convince you that you can encode Turing machines. So you can grab Turing machines, do a bit of processing, and you get out a string exactly representing that Turing machine. A string of zeros and ones in our case, but there are many ways to encode Turing machines. I showed you one. The important thing is that now you know that you can have a complete description of a Turing machine into a string of zeros and ones. So you can express a whole algorithm, a whole computation into a string of zeros and ones. And this concept is really useful now because I'm going to talk about the universal Turing machine. So what's the universal Turing machine? Because you can encode a Turing machine in a string of zeros and ones, you can actually build a machine which reads that string and carries out that computation. So it interprets the string, it interprets the Turing machine encoded in the string, and behaves like that Turing machine. So simulates that Turing machine. Actually, I'll first show you an example of how this works, and then we will talk. We will actually see how what's the workings behind it. I think that with the example you probably be more confident. Okay, so PowerPoint. Then something like this. Yes. So, no, actually, I'll first show you what the copy machine, pattern machine, and terms of distribution machine are. It seems more reasonable. So, it is here. So, first of all, the Turing machine gets as an input the description of the Turing machine you want to simulate, emulate, you want to run, and the description of the input you want this machine to run of, right? So let's say you have the Turing machine recognizing the language 0n, 1n. You shove it inside the universal Turing machine together with the description of the tape you want this Turing machine to run with. And what you get is a simulation of the output of that Turing machine, right? So the universal Turing machine is like something that grabs a Turing machine and simulates it, okay? And it relies on the presence of 3 subroutines. So you need 3 subroutines to run the universal Turing machine. One will be the copying machine. So it's simply a machine which takes a string of ones and puts it on the other side of a marker. So you see it's a copy machine. Copy, paste, copy, paste, copy, paste, copy, paste. Okay? So here I'm using the unary encoding I showed you last time for Turing machines, right? So the copying machine grabs a string of ones and puts it on the other side of some marker. And the first string of ones is also signaled by another marker. So that's very easy. Then you have the pattern match machine. I won't explain it in detail because it will be really long. But what it does is you have a marker telling you what pattern to match. And you try and find that pattern on the other side of another. So you want to match that pattern on the other side of a marker. So here, for example, 1, 1. Does it match with this one? 1, 1? Yes. Then let's see if this one here matches. Does it match? No. So this pattern here and this pattern here doesn't match. Okay. Why do you use that? You use that. I'll show you in a minute. But basically, what you do is trying and find out the right quintuplet, the 5-tuple, to run your universal Turing machine. But so basically, what the pattern match machine does is exactly try and find two strings, two substrings if you want, that match into different parts of the tape. And the third one is the term substitution machine, which instead of copying, it substitutes some terms. So let's say you have a string of 3 ones here, and you want to substitute the string of 4 ones. What it does is just, it erases, it collapses this one, and then it inserts the string to substitute in that place. So now you know the 3 fundamental operation that a universal Turing machine has to carry out. The universal Turing machine tape is divided in 3 parts. In one part, you have the description of the machine you want to simulate. Here you have the description of the tape of that Turing machine. And here you have a small buffer, which the universal Turing machine uses to, well, to simulate the Turing machine. So now I'm going to give you context for all I've said. So, let's say that I have this little stupid Turing machine here. It's really easy. What this Turing machine does is to, if you have an input string with a 0, you rewrite it with a 1. So you just have a 0 and then blanks. You get that, put it into a 1, and then you just accept. If it's anything but a 0, so if you have 0, 0, or 1, or 1, 0, or whatever, it's not only 0 followed by blanks, reject. I don't write down the reject state, but it's there if you know that. So, the universal Turing machine. So you grab this Turing machine here, you encode it with the unary encoding I told you last time, and you put that unary encoding here on the machine description part of the tape. Now, here I'm not using unary encoding. I'm using a higher level encoding so that you can follow more easily. Then you take the input tape, so the input you want to give to this Turing machine here, and you put it in the tape description part of the tape of the universal Turing machine, and then you have the buffer. So, okay, let's see how it goes. So the first thing you need to do is you need to simulate this Turing machine here. You need to copy in the buffer the current state. Okay, so that now the universal Turing machine knows what's the initial state, and it will be Q0. So copy that in the buffer. Okay, so now you know the state. The next thing you need to know is what's the current symbol under the read-write head of this Turing machine here. And it will be 0. So this little marker here means, okay, the head is currently reading a 0. So you copy that as well. Copy machine, activate it, and you copy it in the buffer. So now the universal Turing machine knows that the simulated one is in state Q0 and it is reading 0. Okay? What happens now? Well, we're going through the exact operations we will perform if we were to interpret the workings of this Turing machine with tape 0, 0 blanks. Okay? So what do you do in the beginning? Okay, you're in Q0, you read a 0. What happens if you read a 0, you're in Q0, you rewrite with a 1, and you go right. That's the operation you perform, and that's exactly the operation the Turing machine has to perform to simulate this, right? So, now the universal Turing machine knows the simulated one is in Q0 and it is reading a 0. So what it needs to do is to search in the machine description bit what to do when you have a Q0 and a 0. So now there's a pattern match machine activating. So you search for a quintuplet. And And in this case, the pattern match machine says, yes, I found a match. So there is a rule which tells this Turing machine what to do when there's a Q0 state and a 0 symbol. And now you know with the machine description what to do next. So you go to the symbol you need to rewrite in the tape. You mark it. Okay, the pattern match machine is done. Now you need to substitute this 0 with this 1, because that's the rule you found, right? So we do exactly that. Term substitution machine, go to the next marker, the one in the tape description, tape description part of the tape, and you substitute that symbol. You go back, you move and have a look at what movement this had as performed, which is go right. So you know you have to go right, you apply the rule, and so you move right head of the simulated Turing machine to the right. Okay. Once you do that, you are ready to move to the next state. So you did all these operations here, you want to move to Q1 in the simulated Turing machine, right? So that's exactly what you do. You locate the next state, which will be Q1, and you loop again. So you copy the state, you copy the symbol, you find the right quintuplet, you follow the rules, you copy the state, you copy the symbol, find the quintuplet, you follow the right rules, and that's how you simulate any possible Turing machine. Okay? All possible Turing machines can be simulated by this universal Turing machine, which is the nice thing about it. You cannot do the same with DFAs or PDAs. You don't have a universal DFA running all possible DFAs. No, that's something for the universal Turing machine. So you see, this level of computation is really, really powerful. You can do something that at the other levels you just can't. You cannot run a DFA, whatever DFA, with a DFA. But this universal Turing machine can run every other Turing machine. Okay. So again, you copy the symbol in the buffer, do just that, copied it. Now it's time to find if there's a rule telling you what to do when you're in Q0 and you read a 0. But we see here, there's no such rule. So you're in Q1. If you read a 0, you reject. There's nothing there. So that's exactly what the universal Turing machine has to do, right? So the pattern match machine tries to find for the rule. So tries, okay, the first rule, doesn't work. It's not the same. Pattern doesn't match. Second rule, again, it's not the same. But there's no other rule in the machine description, and in fact, the universal Turing machine rejects exactly like the simulated Turing machine was supposed to. Okay. So this is the universal Turing machine. Do you have any questions? Everything's clear? Okay, cool. So this is how a universal Turing machine works. So, now that you know how it works, I can show you the main loop of the universal Turing machine, which is exactly what I showed you before. So, well, first you initialize the tape, then you copy the current state of the simulated Turing machine into the buffer. If the state is an accept state, and it's easy to know if it is, right? Because in the encoding I gave you, the accept state was always corresponded to 1, if I remember correctly, right? And the reject state corresponded to 2 in the encoding. So if the universal Turing machine finds that the state is represented with a 1, it is an accept state, so the universal Turing machine accepts, because the simulated Turing machine accepts, of course. If it's a reject state, again, you reject. That's, again, in the encoding, I specify that the reject state has a number 2, I think. So if it's neither of those, it means that it's another state. So you have that state in the buffer, you copy the symbol that you find in the tape description in the buffer. So now you have a state and a symbol. So you need to find the right quintuplet over 5 tuple, which tells you, given a state and a symbol, what's the next state and symbol, and what's the movement I need to do. So you copy the scanned symbol into the buffer, and you search for the quintuple. You search for the right rule to apply. Do you find it? Yes, you go on. If you don't find it, you reject. It means that that configuration is not in the rules, so you should reject, as the simulated Turing machine would reject. If you do find it, well, then you have a rule to follow, so you know what to do with those state and symbol. You rewrite the new symbol, and you move head left or right, depending on what the rule is telling you. There's another problem. There's the possibility that you move left too much, and you go, you're not in the tape description side of the tape anymore, but you went too much left, and that's like a segmentation fault error, okay? That's like, yeah, this is not the right section of memory you should be in, so that's an error. So if that happens, reject. If that doesn't happen, that means that you can just locate the next state. That follows from the rules. So you have state, symbol, new symbol, movement. You wrote the symbol, you did the movement, now you have the next state. So you go to the next state, and you begin again with the loop. Okay? So this loop is what the universal Turing machine is doing all the time, until it rejects or accepts. Now, okay, something I want to tell you before going further is that so you can use the universal Turing machine to perform any computation, and the computation you actually perform depends on the input. You have So you can think about Turing, okay, as I told you last time, there's not only Turing machines as a model for computation, but other models of computation have been proposed. The Church-Turing thesis, what it says is that all these models are equivalent. They talk about the same object. They talk about all reasonable computation is captured by these models, and so all reasonable computation is Turing computation. So just to tell you this exists, as Turing machine, you can think about Turing machines as being related to C-like programming, if you want, procedural programming. But there are other paradigms, and specifically the lambda calculus from Church, you can think about it as being in correspondence to functional programming. In fact, it inspired that paradigm. And particularly, it's of interest the fact that somebody took the, somebody really smart found out that lambda calculus could be reduced to just 3, they're called combinators, they're like functions. So different combinations of these functions give rise to universal computation. So you have these 3 functions. It's like having a programming language, a functional programming language, and this programming language is universal. You can perform universal computation. It's Turing complete, okay? Because anything that a Turing machine, that an algorithm can do, these SKI combinators can do, okay? And it's interesting the fact that you have 3 combinators, like you have three subroutines in the universal Turing machine. Okay, so you can really, it's like all computation can be synthesized in a so small number of operators. So all computation is just combinations of SKI or operations of these copying, pattern match, and substitution machine. All computation, everything. That's interesting. So, now, why bothering talking about the Turing machine? Well, one reason is that it's an historical reason. So you need to know that somebody had the idea that a general purpose computer could be built. And that one was Turing. And the very idea of a stored program computer comes from there. So the reason why we're here is because Turing had this idea. I already told you that, but it's good. You memorize it. Another reason why I told you about the universal Turing machine is that now you know that Turing machines implement every conceivable algorithm, arguably, at least the informal notion of algorithm, like we understand it, is perfectly captured by Turing machines. Now you know that Turing machines can call other Turing machines, meaning that you can use Turing machines that you built as subroutines, okay, for other Turing machines. That's of course. So the third thing I want you to know is that you can simulate a Turing machine with another Turing machine. So there's this circularity. So there's no problem building a Turing machine which can simulate another Turing machine. It's perfectly feasible. So now you know these 3 facts. And I'm going to talk again about decision problems. In the beginning of the course, lecture 3, I told you about decision problems. So decision problems are just problems that have 2 possible answers. Yes or no. That's a decision. So is 2 even? Yes. Is 3 even? No. It's a decision problem. Every problem can be restated as a decision problem. So let's talk about decision problems. This is a decision problem in natural language. In a town, there's a barber. This is known as a barber's paradox. So in a town, there's a barber, and this barber shaves all men in town who don't shave themselves. Now, the barber is a man, he's in town. Does the barber shave himself? No? No, I mean, every answer is, try. Yes or no? No? Well, if the barber doesn't shave himself, then he is a man in town who doesn't shave himself, so he should shave himself. And of course, if he does shave himself, he shouldn't. Okay? So he doesn't. And that's circular. Okay? You can reason about this as much as you want. This problem is just undecidable. There's no yes or no answer. Because every answer is paradoxical. This is a paradox. What's the solution? So what's to pinpoint the problem, right? What's the problem of this decision problem? Why is it paradoxical? Because the barber is a man in town. If the barber was out of town, if a barber was from outer space, if the barber was from another town, there would be no problem. It wouldn't be a man in town, just a man, and the barber just shaves men in town who cannot shave themselves. So the barber will be someone, and the question wouldn't be paradoxical, okay? If the barber was out of town, the paradox would be dissolved. There would be no problem with this question. Now let's go to DFA land. I give you another decision problem, which is more, it is nearer to what we're talking about in this course. So, we call this decision problem A DFA, accept DFA if you want. So, given a DFA D and a string W, does D accept W? This is another decision problem. Now, for every problem, you can have different ways to tackle it. Okay, different. For example, we saw that you have different computation models, models of computation. Now, certain models can tackle this question without being paradoxical. But if you want to tackle this question with a DFA, if you want to compute the answer with a DFA, you reach a paradox. So, I restate the question as in DFA land, where all machines are DFA, there's a machine, and that machine accepts all DFA which don't accept themselves. What does this mean? How can a DFA accept itself? Well, as I did with the Turing machines, you can encode the DFA in a string. Okay, you do almost exactly the same procedure I did for Turing machines, and you encode the DFA in a string. And if you feed this string to some DFA, that DFA could accept it or not, right? And so what happens when you feed the description of a DFA to the same DFA? Does it accept the description? Does it not? This machine here, a machine that accepts all DFAs which don't accept themselves, is paradoxical. For the same reason why the Barber's paradox comes to existence. So if the machine accepts itself, it shouldn't. If it doesn't, then it should. You see, it's circular. Well, not circular, but it's a paradox. So what's the solution? What was the solution of the Barber's paradox? Move the Barber out of town. So what would be the solution to tackle this problem here? Move away from DFA land. So instead of using a DFA, grab some Turing machine that can do the work. Okay? So go to TM land. Well, okay, a Turing machine can be built, of course. You can build a Turing machine to decide if DFA accepts itself, right? It's really, really easy. You can decide if any DFA accepts itself, right? You grab the DFA, you encode it, and you feed the input to the DFA, and you see what happens. There's only two options. Either it accepts or it doesn't. There's no other option, right? So if it accepts, then very well. If it doesn't, okay. So you can build a Turing. You can think about an algorithm to tackle that problem. So you can build a Turing machine. So there's no problem. But now we're in TM land. So we have another decision problem. We will call it ATM or accept TM. Given a Turing machine M and the string W, does M accept W? I think I wasn't clear in this one. Okay, so I gave you the Barber's paradox for DFAs, and the Barber paradox for DFAs implies that this decision problem here will be undecidable if you were to use only DFAs. Okay. In case of Turing machines, the problem is you can have the same paradox, but you cannot move out of TM land. Well, not in the definition of reasonable computation. So that means that if I give you a TM Turing machine M and a string W, the problem of does M accept W, is it decidable? Is it not decidable? The problem is, if it is not decidable, then you have to live with that. It's just not decidable. It's just a problem you cannot give any answer to, because you don't have anything better than a Turing machine to tackle it. You cannot move outside the TM land. So I want to prove to you that it is not decidable. The way I do it is by using a variant of Cantor's diagonal argument, which I showed you last time. I showed you to prove that real numbers are more infinite than natural numbers. So, and that there are more real numbers than Turing machines, so there are real numbers which cannot be computed by any Turing machine. So, what I do here is I make a list of all possible Turing machines. I can do it easily. I can give an order to them because I can find an encoding of a Turing machine. Then I just sort that list. Okay? So, and then I want to see what happens if I feed the Turing machine the description of another Turing machine. So there are three options. Either it accepts, it rejects, or it can loop forever. Now, I just want to know if it accepts or not. So if I have Turing machine M1 and I feed the description of Turing machine M1, does it accept? Yeah, maybe. Accept. This one accepts. If I feed it the description of Turing machine M2, does it accept? Well, no. Okay, so you can make a table. You can feed the description, and some will accept, some will not accept. So, well, one will then say, to answer this decision problem here, given a TM M and a string W, does M accept W? Well, if that machine exists, then of course I can have a machine telling me what happens in this diagonal here, right? So if I feed M1, the description for M1, I will have a Turing machine which tells me that accepts, okay? So just simulate M1 with the description M1 and see what happens. Accept, okay. That Turing, so my solution for this problem, if there's a solution for this problem here, it has to be an algorithm. An algorithm is a Turing machine. So I have a Turing machine telling me what happens in this diagonal. So I have a Turing machine recognizing all that happens in this diagonal. So I give the Turing machine some other Turing machine as an input. So I give this decider a Turing machine as an input, and the decider tells me, yes, this Turing machine accepts itself. No, this Turing machine doesn't accept itself. Okay? It's an algorithm. It can do that, right? The problem is that if you have such a Turing machine, then you will have another Turing machine which does exactly the opposite. So let's say I have a Turing machine, let's call it AX. Okay? So you feed it the description of another Turing machine, and it tells you, yes, it does accept itself, or no, it doesn't accept itself. Let's say yes or no. But then I can easily build another algorithm which does the same. So an algorithm which has X as a subroutine, but then it grabs this yes and it makes it a no, grabs this no and makes it a yes. So if the subroutine CC would accept, then reject. If it would reject, then accept. I know it's very circular. So this machine here would accept all Turing machines which do not accept themselves. You can easily see, well, you can see that this will solve the barber's paradox, let's say, right? So this will be a Turing machine accepting all Turing machines that don't accept themselves. But then you ask yourself a question. Okay, this is a Turing machine, we call it ACK. What happens if I give it as an input its own description? You have its own description, right? You're saying you can build it, so if you can build it, you can encode it in some number. You take that number, and you put it as an input. What happens here? It just explodes. It doesn't give you anything. I mean, it's impossible. It's a paradox. Because if it accepts its own description, it should reject. If it doesn't, it should accept. You see, it's the same paradox as the barber paradox. So this machine cannot exist here. But if this machine cannot exist, then this machine cannot exist. So I cannot build a machine which tells me if a machine accepts itself or not. But if I cannot build that, that means that I cannot solve this general problem. So given a TM n and the string w, does n accept w? I do not have an algorithm to answer this question. Because if I had that algorithm, I could put, as a w, I could put the machine description, and that would lead to all the paradoxes which we saw. So this problem here is undecidable. So I want some questions, because I look at you and I see you really confused. So please ask me some questions.
Just reminds me of the little set thing where it basically says set complement. So is it the same thing? Just in a different form?
Yep. It is exactly the same. And the book got the Lesker back, right?
That's what it goes into. Yeah.
So please ask me some questions. So if something is not clear, that's the right time to make it clear.
Could the universal Turing machine simulate itself?
Yeah, why not? Yeah. That's something I thought about, right? I see no problem with that. So you grab a universal Turing machine. That you can encode it, of course, because it is an existing Turing machine, and you use it inside the universal Turing machine, and that does exactly the same operations. Yeah, there's no problem with that. I will say you could emulate a universal Turing machine with another encoding, so that would make the original Turing machine like an emulator. That's interesting. Thanks. So let me go through this again. So my decision problem is, I give you a Turing machine, I give you a string, and you tell me, using an algorithm, so you program some code, you take the Turing machine and W as an input, and you tell me, yes, this Turing machine will accept W. It seems like an easy problem, okay? Meaning that from a programmer perspective, as soon as you hear this problem, you should, try and make up a solution. Yeah, I could think about, no, it cannot be solved. It's undecidable. So if you think you have a solution, you're just wrong. And the reason why it is that if you have a solution, okay, so if you can tell me with absolute certainty for any Turing machine and any W with your program, if you can tell me that the Turing machine accepts or it doesn't accept that string, then you can feed the Turing machines their own description number, and you can answer. You can tell me, yes, it accepts, no, it doesn't, yes, it accepts, no, it doesn't. If you can do that, you can build another Turing machine, as I showed you, that does just exactly the opposite of the program you programmed for me. So it takes your program, it reads the output, and it does exactly the opposite. And that's another Turing machine. So you can have a number, and you can fit this number to itself. And once you do that, you create the Barber paradox. You cannot escape. So once you do that, you just can't give an answer. So is the barber shaving? Does the barber shave it himself? You cannot say yes. You cannot say no. You cannot say anything. Here, does this machine accept itself? Well, if it does accept itself, okay, that would mean that it has to say no. If it doesn't, then this will say no. So this says yes, it does. So if it doesn't, it does. If it does, it doesn't. This is a paradox. You cannot escape. So this language here, ATM, or equivalently this decision problem here, accept TM, is undecidable. No escape. So there's no general procedure to tell if an answer to some problems is yes. Okay, you say, with your programmer mind, you say, okay, I'm a little sad that I cannot solve this problem, but maybe I can step down a notch and maybe solve a simpler problem. So, can you at least tell if an answer can be found for a decision problem? So you don't tell me if the answer is yes, you don't tell me if the answer is no, you just tell me, can an answer be found? Is the problem decidable? Can an answer be found? So, given a decision problem, can you tell if you can find an answer? Ever. What's your guess? Can you solve this problem here?
Not yet.
Yeah. Who said yes? No, I'm sorry. But that's a good attitude for a programmer, though. So, what I described to you is the halting problem. It's a very famous problem in computer science, right? Probably the most famous. So what does it mean to halt? Halt. So at the end, you can do three things with its input, right? It can either accept, it can reject, or it can loop forever. There's only three possibilities. So if you observe a Turing machine with some input, this Turing machine, you will observe it either accept, reject, or if you live forever, you will see it loop forever. So if it accepts or rejects, then that means it halts. So at a certain point, it stops. It doesn't matter what it says, but at least it stops. So when you say halt, it means, yeah, the TM at a certain point carries out the computation and gives you an answer. The second possibility is that the machine can loop forever, so if it doesn't halt, it keeps running forever. So, a way to rephrase the problem from before is there a general procedure to know, given a Turing machine M and an input string X, if M will halt with input X? We will answer that in the next hour, so do a 10 minutes break. We saw a decision problem, which was, can you tell if a Turing machine accepts some strings? So do you have a general algorithm? Can you program me something that tells me, okay, give me a Turing machine, give me a string, and I tell you if it accepts or not? No, you can't. As I showed you, if you had that machine, if you had that algorithm, if you had that program, if you could program that thing, that would lead to paradoxes. So I can tell you with absolute certainty you cannot do it. Otherwise nothing would make sense anymore. So another problem, which is somehow lesser, but very interesting, is, okay, let's forget about acceptance of strings. Let's solve another problem, which is, can you tell if a Turing machine will halt on a string? So I give you a Turing machine, I give you a string, and you write me some software which solves for every Turing machine, and it tells me, okay, for this Turing machine holds. For that Turing machine doesn't. Can you write an algorithm like that? So how do we make this more formal? Well, we have a formal definition of algorithm, which is that of Turing machines. So let's rephrase it. Is there a general procedure, so a Turing machine, to know, given a Turing machine M and an input string X, if M will hold with input X? Is there a Turing machine H, hold, which takes as an input the description of another Turing machine M and an input string X, and as an output it gives me accept if M holds with X and reject if M doesn't hold with X. So if M loops forever, my H Turing machine rejects. If it doesn't loop forever, it accepts. So can I build this? Okay, let's assume I can build that and see what the consequences are. So let's say I can build H. So this is more or less what H does. Have a Turing machine, you have an input, and you print 0 if it loops forever. I'm doing this just for clarity. You don't need to print anything, but because I'm going to do some composition of machines. The fact that this prints is it's easier to explain to you. So it prints 0 if the machine TM loops forever, or it prints 1 if it doesn't. So if it holds. So 1, 2. I'm going to tell you about other two Turing machines, which we can absolutely build very easily. I call this the negator. It sounds really cool. So the negator N, if you input a 0, it gives you a 1. If you input a 1, it gives you a 0. Oh no, actually, sorry. If you input a 0, accept and print OK. Why did I call it the negator then? I don't know. So if you put 0, then it just prints OK. So remember that 0 in the other machine, when it printed 0, it means that it was looping forever. In this case, if it receives a 0, that's why I called it a negator. I remember. So if it takes a 0 in input, it prints OK, it accepts, holds, no problem. If it receives a 1, it loops forever. So you have some, I don't know, this machine has if x is equal to 1, open a while, and just close it. So while forever. It loops forever. Okay? And another simple one, and this I know why I call it a photocopier. It takes an x, something as an input, and it's just duplicated. So you have two outputs, x and x. So you're saying you can build me H. You're saying, Giovanni, I love your specifications. I have an algorithm for H. It's 500 pounds. And I'll tell you why I don't believe you, and you just want to get my money. So, if you had H, you can have something like this. So, photocopier machine. This is the opposite. So the photocopier machine copies whatever x I have into two. You get it, like here you have a tape which is split in the middle. It doesn't matter. You just have two copies of x, right? And you feed that into the machine H, and H either accepts or rejects. In case it accepts, it gives you a 1. Yes. So it gives you either a 0 or a 1, right? you input this to the negator machine, and the negator machine either prints out OK or it loops forever. If, okay, let's do, if 0, it prints OK. If 1, loop. Right? So if you had H, if you had an algorithm, H, solving the halting problem, I could totally build this machine, right? So the photocopy machine, you can have an algorithm that does just that. It's easy, right? The negator machine, even easier. I don't have to prove you that you can. You're a computer scientist. You can easily, in 2 minutes, program a P machine and an N machine. It's really, really simple. But this is now another Turing machine, right? So this is another algorithm. So you can think about this machine as being machine S. You can think about this as being subroutines. I showed you that you can have subroutines in Turing machines, right? And this is just another Turing machine. We call it S. So what happens if you feed S to S? So this is the description number. Again, the Barber's paradox. So S, P photocopies S here and here. And the halting machine, H machine, has to decide whether S halts with string S. So this is the decision. You have two possibilities. Either it halts, so S halts when you feed it S. So you have a 1, and in this case the negator machine loops forever. So you're saying it halts, but the machine loops forever. The other possibility is that, okay, H responds, no, S loops forever when you input S. But that's wrong, because the negator machine then accepts and prints OK. So it halts. You see? So something is wrong here. So I can build a P machine, I can build the N machine. Why is this paradoxical? Well, there's only one possibility. I cannot build the H machine. So there's no way I can have an algorithm that decides whether a given Turing machine halts with a string or not. Of course, you may think, that's a nice thought I had. And as soon as I had it, I told myself I'm really stupid, which is, okay, I don't have a halting machine that solves the general problem, but maybe I can solve specific problems, right? So I have specific halting machines solving specific classes of Turing machines. And then I get them all together, and I can solve the halting problem. Well, of course, that's wrong. Because if you had specific halting machines for specific classes of Turing machines, and so with this battery of algorithms, you can solve the general halting problem. You can see this battery of algorithms like another algorithm, right? It's like, so what I'm trying to say is that there are infinite ways a machine can loop forever. So there's no way, if you spend all your life trying to build H, and you build many sub-H machines that solve a class of algorithms. So that tells me for a class of algorithms, this will halt, this will not. You still leave out the majority of all algorithms, an infinite amount of algorithms you cannot answer. So H, the halting problem, is undecidable as well. So if I ask you now, can you at least tell if an answer can be found? Given a decision problem, can you tell if you can find an answer? The answer is no. So you have no general algorithm to know if an other algorithm will stop. ever. That's quite powerful. That's a problem you would like to solve, right? It's not as abstracted as it's not as abstracted as the other problems I showed you. This is really real. You would really like to have a compiler telling you, Giovanni, if you have this line of code here, your program will never halt. What are you trying to do, right? You just kind of have a general algorithm that always tells you that. You can have specific algorithms solving some of that, but not a general one. So, I showed you a proof that H cannot exist. There is another, and by talking about this, I will tell you about reducibility. Okay, so some problems you can reduce to other problems. So, what does it mean? If you have problem A, and problem A reduces to problem B, that means if you find a solution to problem B, you solve A as well. It's an easy concept, right? So if you solve B, A reduces to B, so if you solve B, you solve A as well. Now, if you solve the halting problem, right, I show you that you solve ATM as well, so the acceptance problem. Does a machine accept W? Why is that? Well, it's easy. So, instead of running, okay, so you have a TM, you have some string. H will tell you if the TM will halt with a W. Well, if it doesn't halt, right? So it doesn't, then reject. If it does, if H halts with W, if it halts, what can you do now? Well, if it halts, it's perfectly fine. You just simulate TM with W. It halts, so you know in a finite time you will know the answer, right? So you will know. So now run TM with W, and you will know if it accepts or rejects, right? So if you have H, it's really easy to solve A, TM, right? Because, okay, if the machine you halts with that string, you just simulate it. You know you can build a universal Turing machine. I showed you can. So you just simulate it with that string, and if it accepts, very well, you solve the problem. But that's not the case, right? So because we know ATM can't be solved, I showed you that it's just a logical paradox if you solve it, then H cannot exist. It's simple as that. So you say that ATM is reducible to TM halt, right? Now, why did Alan Turing think about these questions? Why did he spend any time at all trying to answer these questions, right? Because actually he showed that the halting problem is reducible to the Entscheidungs problem. I don't know if you remember. You read it? So I don't know if you remember, but this all started because Hilbert had a couple of questions for mathematicians. He had a problem. He wanted to know if there was a way to have a formal system which was complete. So all true statements could be derived by the axioms. If you can have one which is complete, consistent, meaning that there's no way you can derive a false axiom a false statement from the axiom. Actually, that sounds, consistent, it means that you cannot derive something and its opposite. So you cannot derive that, I don't know, 1 is less or equal than 2 and 1 is greater than 2. You can derive those two. They're mutually exclusive, right? So a consistent system doesn't have this problem. The third problem Hilbert proposed was called the unshiding problem, which literally means the decision problem. So if I give you a statement in predicate logic, so if I give you a statement in my formal system, can you tell me if it's provable or not? At least tell me if it's provable, right? I don't want to know if, I don't want the proof. I just want to know if it's provable. At least that, so I can work on it, right? And the answer is no. There's no general procedure to apply to a statement, to any statement, and say this is provable. This you can decide. You can decide it, right? I think that the proof is a little involved. Proof that the halting problem reduces to the unshiding problem, right? But it boils down to this. You can build this statement in predicate logic. So you can say, so M holds with W as input, if and only if, and then some tautology, so 1 equal to 1, right? So if you had the general procedure to know if this is provable, then you will solve the halting problem. And I just showed you that the halting problem is unsolvable. And so, you know, the unshiding problem is unsolvable. There's no general procedure to know if a statement can be proven, so if it comes from the axiom or not, right? Well, this sounds really abstract. And it is in a way, because we're talking about the very foundation of mathematics here. But, as often happens in mathematics, this has very powerful consequences for us, okay, for computer science and for your activity as problem solvers, as programmers, as computer scientists. So, there's a whole range of questions which cannot be answered. A whole range of questions which you would like to answer, actually. You would really like to have an answer to those questions, to build an algorithm spitting out the answer to those questions. But you just can't. So, for example, is there a general way to tell if a given program, so a Turing machine, will ever print 0? It looks harmless, like a harmless problem, okay? It really looks harmless, but no, you cannot. You cannot answer these questions. This question generally. There's no way you can build an algorithm taking my code and telling me it will print 0 at some point. Because if you could do that, you could solve the halting problem. This is the beauty of reducibility. So the fact that you can reduce some problems to some others. So if you solve those, so why TM halt? So the halting problem can be reduced to this one. So for every Turing machine, right, with every string, so really these guys, you can build these other Turing machines. So if these halts print 0. So this is a Turing machine, right? What you're doing is, if you had a solution to this problem, so the problem is, can you tell me if this algorithm will ever print 0? If you add this, you could build a machine like this. So a machine that simulates some TM, some Turing machine, with some string, and if it holds, it prints 0. So if you could give an answer to this, right? So this is a piece of code. You put it in your algorithm, and your algorithm tells you, yes, this program here prints 0. Then you know that this TM here holds with W. So you solve the Halting problem because you can put whatever TM, whatever W, right? You can just build software which has some algorithm, runs some algorithm with some input, and if it holds, print 0. So if you can answer this question, you can have an answer to the halting problem. You see? It really ripples, this undecidability ripples through all computer science. So, okay, let's see can you tell if the language accepted by a certain Turing machine, so you have a Turing machine, whatever, your algorithm, the language accepted by this Turing machine, is it non-regular? Is it context-free? Is it finite? You cannot answer these questions for the exact same reason. You can reduce your problem to the halting problem. Sorry, you can reduce the halting problem to your problem, meaning that if you have a program which tells me, okay, this Turing machine accepts a regular language, you can build, well, in this case, a non-regular language. You can build a Turing machine which has some simulated DFA here, which runs if and only if this other simulated Turing machine holds. So you build it. You build some Turing machine which first simulates TM with input W, and if it holds, simulates a DFA, right? With input X. So if you can tell me, if you have an algorithm which can tell me if this Turing machine accepts non-regular language, then you solve the halting problem. Because if this holds, then you have a DFA here, right? So that means, oh, started to work just now. If this holds, then you have a DFA, a simulated DFA. A simulated DFA, of course, accepts a regular language, right? So the answer here will be regular. So if you can tell if this Turing machine accepts a regular language, then you know this halted. And you can build this as however you want, right? So you can make it general, and you can solve the halting problem again. So this is not possible. And same goes for, is my language context-free? So is the language of my Turing machine context-free? Is the language of my Turing machine finite? Is my language a language composed only by prime numbers? These are all undecidable questions. Okay. That means that you cannot build, as I said, any general algorithm. You can answer for some algorithms. You can answer, right? But it's like every time you need to start from scratch. You don't have a general solution. You don't have some software ready telling me if any Turing machine accepts only prime numbers. Okay, that's impossible. And even more interest is that any non-trivial property of the language accepted by a Turing machine is undecidable. What is a non-trivial property? A trivial property is something that all Turing machines have, some property that all Turing machines have, or none of them have, right? So it's trivial. For that property, either all Turing machines have it, or they don't, any of them. A non-trivial property is a property that some Turing machines have, and some Turing machines don't have, okay? And if all those properties, you cannot have a general algorithm. That's just, that's a huge result. This is called Rice's theorem. That's a huge result. That really tells you about the limitations of what you're doing. And now, again, you may think this is all very abstract. It is not. This is really, really concrete. Okay? So, for example, these are some questions you cannot write an algorithm to answer, a general algorithm. Is a program correct? What does it mean? Is this program actually giving me the output I wanted to give me? Right? This is why you do unit testing, right? You wouldn't have to do that if there was a way to have that algorithm there, right? No unit testing. You just pull it, shove it into another algorithm, and that algorithm tells you, yeah, this is not correct, you did a mistake. So there's no general algorithm for that. Are two programs equivalent? So we have a programming competition. We solve the same problem. We write slightly different programs, maybe. And the judges say, okay, let's run these two programs into my general algorithm to tell me if they compute the same function, if they do exactly the same thing. Nope, there cannot be such a program. It's a shame, right? Is a program optimal? Oh, that's so a good question, right? If you had an algorithm to answer that, that would be so great, okay? For all engineering, all mathematics, would be really awesome, right? You cannot answer. There's no general algorithm, I'm sorry. There's no way you can write that. Is a program a virus? Another $1 billion question. If you could have an antivirus which was capable of just, okay, let's read this code. Yeah, this is a virus. This is not a virus. Okay, you will need Avast to stop you during the game, saying Avast has to update, right? That would be great, at least for me. I always get a stroke every time it goes. So you cannot even answer these questions. So now you see the importance of understanding computation theory. If you didn't know this, you will say, hey, Matt, let's do a startup. Let's build the most awesome antivirus ever built. My antivirus will recognize every virus in the world. I have this fantastic idea, right? And Matt attended my lectures, and Matt will say, yeah, you didn't understand anything. You cannot build such an antivirus, and we're not going to do a startup for that. So, as you see, computation theory really informs you about the limits of computation. You cannot just solve any problem. There are some problems which cannot be solved theoretically. You can prove they cannot be solved. And that's a bummer, but now you have, this is an introduction, but now you have the tools to get into that mindset. So you know that your computers are not all powerful, and that what you're doing has limitations, and you have to be aware of that limitations in order to be a better computer scientist. Because if you're aware that there's some things that you really cannot do, that your computer cannot just solve any problem, you become a better computer scientist, because you know what problems you can tackle and what problems you can't tackle. And they showed you there are some problems that one would really like to be able to tackle, but they cannot be tackled. And now you know that if you ever find yourself thinking questions of such a huge how to say that? I mean, if you had an answer to these questions, you would really rock the computer science world, right? Anytime you think about questions of this form, now you can start and think, okay, can I build a general algorithm to do this? Let's see if I can find a way to reduce my problem to the Halting problem, for example. Because if you can, a way to reduce the Halting problem to my problem. Because if you can, then that means that your question cannot be answered. You won't spend time trying to answer an answerable question. So, what's the problem here? The problem here is that you're using Turing machines to reason about Turing machines. Okay? It's another example of the circularity of language. So language itself is bounded, it's limited. Like Gödel showed, right? Gödel used another wormhole, another circular property of language to show that languages, formal languages of a certain power, cannot be at the same time complete and consistent. And now Turing shows that some languages are not, decidable. That for some formal systems, you cannot have general procedures to decide its statements. So now, a student just during the break asked me a question. Can we move outside the TM land? Is there a way to go outside that? Okay. Is there a way to not be circular, to not fall again in the barber's paradox? Again, we don't know. Some people think we can. Some people think we will never be able to. That's really a fundamental question. So it boils down to, is there anything resembling super Turing computation? Do you have another level? So at this time, we're here. So there are regular languages, then you have context-free languages, context-sensitive languages, then you have Turing decidable languages, so you can build a Turing machine to say yes or not, to accept if a string is in the language, to reject if it is not. Then you have Turing recognizable languages, which means if the string is in the language, accept. If it is not, either you reject or you look forever, you don't know. So is there anything outside that? Can you go beyond? So 2 weeks ago, I skimmed through a paper of this physicist. So I skimmed through the paper because I didn't know physics. So I wasn't able to actually understand it fully. But this physicist basically proved that if you had, if the universe responded to the Newton laws of movement, then you could build a machine respecting those laws, solving the halting problem. So infinite time telling you if a given Turing machine will halt or not with a given input. Okay. To do that, this physicist required infinite energy and continuous space. And of course, the machine is not feasible in any way in the physical world. First of all, because we know the Newton laws of physics do not really capture exactly what's happening in our universe. But if they did, we wouldn't have infinite energy anyway. So, but we don't know. Maybe someday somebody will discover another model of computation. Nobody really knows how this model would look like, or if it's even there. But if it is, then we will be able to move beyond Turing machines, and we will be able to solve all these problems here. And that would be really neat. But again, we have no idea if that's possible. Actually, just because